Welcome to Chapter 1B of the HDX PRO tutorial. In this segment, we'll walk through how to create a new project. You'll learn how to add your proteins and define their states, set up labeling time points, import data files, choose a data acquisition mode, and upload a peptide list. We'll finish with a look at the project summary and structure, so you're fully set up to begin your HDX analysis. Let's get started.
To start a new project, just click the HD Examiner Pro button on the Start page. A window will pop up that will ask you to set a name and a location for your project. To change the location, just click the Browse button and select the folder on your computer and give the project the name that you would like to set. Once you click OK, the project creation wizard will pop up. The first step is to add your proteins to your project. You can do this in multiple ways. One way is to select the FASTA file from your computer that has the protein sequence or the proteins. Or you can select the PDB or multiple PDB files from your computer that contains the 3D structure, and it is useful if you ever want to model the 3D structure and paint the HDX deuteration values on the structure. You can also use this fetch PDB code button where you can just enter the code of a PDB if you know it, and it'll fetch it from the protein data bank. Once the protein is added, you'll see that its sequence is now visible if you hover over this button. Once you've added your proteins, just click the Next button. In this step, we will be adding our protein states to our project. A protein state is simply a condition, but it's also just a label for how you want to categorize your project. For example, if you're doing comparative analysis, you might want to add 2 states. Or if you're doing a comparative analysis of one antigen versus many targets, you can add as many protein states as you need. In this example, I'll just be setting up a 2-state project, where one of the states is going to be named APO, and the other one will be called HOLO. And I'll be setting a default control here, just so that in my visualizations, they will be preset with one of the states to compare against. Next up, we will be adding our labeling time points. Just as before, you can add as many time points as you wish to have in your project. And this project, I'll just be setting up a 2 time point experiment. One with 120 seconds, and the other one with 1200 seconds. And I'm also going to be setting the D2O concentration. In this case, I'll be leaving it at 50% just because that's the actual D2O used in solution for this. But you should set this to the D2O concentration that you're using. This value is going to be used in correcting some of the calculations down the road. Whenever we're reporting percent deuteration, that value will be corrected by this D2O concentration that you're using. Now we will be adding our data files. To do that, just navigate to the folder that contains your data files by using the Browse button. Make sure that you select the folder that contains your data files, that is the parent folder, especially in cases where your data files are actually folders themselves. That can happen, well, that is the case for Waters data files, and for Agilent.d data files, they are folders. So just ensure that the path that you set in the location is the parent folder that contains either the .raw data files or .d or whatever data file you're using. Make sure that the data provider is selected according to the data that you're acquiring. In this case, there are 2 options, the internal data provider for converted files and a thermo data provider. There will be more data providers available in the future. For now, I'm going to be using thermo data. Don't worry about converting the data. The thermo data provider has a very efficient method of reading the data. And so now what I'll be doing is I'll be adding the respective replicates in each time point and condition under the correct area of my project tree. So for example, the 1200 and the 120 seconds of the hollow state, as well as the 120 seconds and the 1200 seconds of the APO state. So now I have all of my data files set up in the project tree. Just click Next. At this step, you can select whether or not you're doing HXDIA. If you're doing conventional analysis, then you don't have to set up any other properties of the files. However, if you're using DIA data, just set up the type of fragmentation that your instrument is doing. And in this case, because we want to ensure that the peptides are fully scrambled in MS2 so that we can measure the deuteration multiple times, the two options presented here will be CID and HCD. In this case, I'm going to be leaving the HCD type of fragmentation selected. By the way, if you have DIA data, you can also do a conventional style HDX analysis because MS1 data is being carried in the files anyway. In the final step, we will be adding our peptide list to the project. This is done via a CSV format, just the same way it's done in the regular HD examiner, where the CSV format has a particular set of columns that it requires to see. The minimal amount of columns that you should provide are the sequence, the charge, and the retention time. This is all that would be required to actually find the peptide in the data files. The sequence and charge will be used to generate the composition that we expect the molecule to have, and so we'll be able to find the molecule that way. You can also define its mass directly. Then it'll look at exactly that mass. Start and stop can be provided. The protein can be provided. This is more important if you have multiple proteins, then each peptide should have its protein source. The software will check anyway whether a peptide sequence is contained inside of a protein sequence. So it's going to double check that the peptides are assigned to the correct proteins. But if you have the protein information and it matches the name of the proteins in the FASTA file, then you can define them in the protein column. But again, just as a minimum, just provide the sequence, charge, and retention time of your peptides. The data format that can be used is what I'm showing you here with the capital letters, but you can also provide PLGS data. You can also provide bionic peptide list and MS Fragger. There's a couple of there's a few formats that the software can recognize in a peptide CSV format. Also, when you have your peptide list, please ensure that every entry is a single row. So for example, if this peptide was identified by a search algorithm at multiple times in a mapping file, it is good to combine those multiple identifications into one and average its retention time so that you don't have the same peptide repeating many times, because they will appear as separate entries in your peptides table. So always make sure that your peptides are single entries. That is, a sequence and a charge should be a unique entry. In this window, we also have the ability to set up transitions. I will cover this, its functionality, but I don't recommend people to be using this unless you know exactly what you're doing and you have a very specific method to select the fragments that you want the DIA method to look at. The default is that the software will generate fragments for every peptide here and just search for every fragment possible. But if you have a method to select, let's say pre-select 5 fragments that you want to look at for every single peptide, that can be done in this type of format. And the documentation will describe the exact format needed here. For now, I will not be doing this, and I don't recommend doing this unless, again, you have a specific method. Click Next. The summary view will just give you kind of a top-down picture of your project setup. If there's any issues with the project setup, they will appear as warnings or error or information next to each step. And you can also click on each step to navigate to that point in the wizard as well. If everything looks good, then all you have to do is just click Finish, and then the project will move over every data file into your project so that your project becomes portable. Once the data files are moved over and the project is created, you'll be presented with a blank project where you can start the data analysis right away. The next step is to begin processing your data. But before I get there, I'd like to just introduce the project structure here on the left side. On the left side of the screen, you have your project that you've set up during the wizard with all your data files. The data files are browsable. If you double click one, you can actually see the TIC and you can actually see individual spectra, MS1 and MS2. There's a couple of functions that you can do. You can integrate some data if you're interested in a particular region of the TIC. And you can also do XIC extractions directly from the MS1 data. That works in MS1 and MS2. In this case, I have a DIA file, so my precursors are going to be the individual DIA windows. Okay, the rest of the project tree is going to have my proteins and my peptides. This is a dummy project, so my peptides don't show up, but when you create your project, your peptides will appear as a collapsed list here that you can click and see. As well, there's a results section here where after you process your data, each individual result will be added to the project here, and you can have as many as you would need. And why individual results? Because you can process the data in different ways with different parameters and do different manipulations to each separate result.
Now that your HDX project is fully set up, you're ready to move on to the next step, processing your data. In Chapter 2, we'll show you how to set up processing parameters and give you a high-level overview of what the HDX data processing workflow looks like and what kind of results you can expect. When you're ready, let's continue.